What's up, guys? Today we are going to discuss about the ChatGPT-like system. When you type a question on the ChatGPT and within few seconds, a thoughtful, detailed answer appears word by word and token by token. That is ChatGPT. But behind that simple chat interface, there's one of the most complex distributed systems ever built. We're talking about a system that serves 100 million users and handles 10 million plus messages per day. It runs inference on models with hundreds of billions of parameters. How do you design a system like this? Let's deep dive into it. Now, when an interview starts, you're supposed to write the functional requirement first. Best thing is you ask questions, what all will be the functional requirement? There are chances that the interviewer might have missed something to write in the question and it might be in his mind. In this case, I'm taking almost all the functional requirements that can be covered in an interview like session. We will have multi-turn conversation. In ChatGPT, when you ask something, suppose you say hi, it replies back with a relevant answer. It is multi-turn conversation where the ChatGPT knows whose turn it is, then stream process responses. These systems are real-time responses. The tokens need to be sent in real time. That is why we use streaming system in this case. Then multimodal supports. We are not only using the latest model, we might want to use some other model, maybe Opus or Sonnet or somewhere by GPT. Basically, we want to make sure that we are using appropriate model for appropriate kind of question. We are not using the expensive ones for the very simple queries, and we are not using very simple ones for our complex queries. That way, we can work on the cost optimization. System prompts. This allows the custom instructions per session. Maybe we want a different system environment for a particular prompt. We can load it into a system file or image upload. Sometimes we want to do image editing or we want to upload a file to be analyzed. This way, we want to support multi-modal input support that supports text as well as file system, conversation history. Maybe you want to save the conversation history so that someday you can come back and discuss about that conversation. You wanted to store that in different tabs and you can use it. Again, plugins and tool use. Plugins like Calculator or Google Sheets, if you want to connect it to different types of plugin for different use cases, there are MCPs. You use the MCP tokens to connect to different tools and use it while the AI is working for you. User management relates to the accounts that a user has created, the type of billing, if it's a free user or a pro user. Based upon that, you want to do the user management. You want to prioritize certain requests from paid users as compared to the free tier users. Content moderation. Many cases, we want to filter the harmful inputs. Maybe there are some jargons or bad language that we want to filter out. We want to make sure even the output that the ChatGPT or AI is giving, that is having a filter content, not very bad words or not something that is against the law. We want to give API access for the systems we want. Now let's come to the non-functional requirements. In a system design interview, you are required to cover up non-functional requirement, even though if it is not explicitly mentioned in the question. You need to make sure that you're covering all the non-functional requirement, speak about your thought process, and confirm with the interviewer. Let me take some of the non-functional requirement in this case. We want to maintain a latency. We don't want the response to take a lot of time, but I'm okay to get a response within 1 second or less than that. In that, we will have first metric called time to first token. That is how much time it takes to respond for the first token. It should be less than 500 milliseconds. And then we want to maintain a streaming rate of around 30 to 50 tokens per second. That way, we can keep the conversation going on. We want to make sure the availability time is 99.9% uptime. Scalability is the most important thing in distributed system. We want to make sure that we can handle 100K plus concurrent sessions. Let's take this scale number for this system design. For this interview, we can take the throughput to be 10 million plus messages per day. It should be able to handle 10 million messages. Now, security is very important. We don't want to strain on PII data of the users. We want to mask them. Security is of utmost importance. We don't want the sensitive data to be stored on the servers that it can be utilized somewhere else. Apart from that, we need a cost efficiency. Cost efficiency involves the GPU utilization, and GPUs can be very expensive. We want to make sure that we are doing optimum GPU utilization. That way, We don't waste the resources. We can concurrently handle multiple requests. That way we can do cost efficiency. Now let's take cap theorem. In this, more than consistency, we want the system to be available and be able to tolerate the partitions. That is why we will take availability and partition tolerance as compared to consistency. Consistency is least important in this case because even if we lose some of the conversation data, it's fine with us because it's not a transaction data. A slight delayed response is acceptable, but going down of the system is not important. As a senior engineer or a staff engineer or higher role, it is good to discuss about the capacity estimation. This will prove that you are good candidate for a staff plus roles. We can discuss about the capacity estimation. Let's start with the number of users. As we can have 10 million daily active users, we should ask from the interviewer what is the registered user and daily active user. Based upon that, we can show the calculation. In that case, if we have 10 million daily active users and 100 million registered users, average message around 5 message in one session, it means we will have 100 million messages per day. Let's talk about the QPS. QPS is queries per second. We will have 100 million queries per second, assuming that 100 million registered users are logging in every day, divided by the total number of seconds in a day, which is almost equal to 1160 QPS on an average. If it's a peak time, maybe the peak time of the day, there it could be a rise in 3x numbers. In that case, we will use 3500 QPS. Now, token is a very important part of AI systems. We need to, in terms of token, average input is 500 tokens. What about the average output? For 500 tokens, the average output is usually around 800 tokens. How many total tokens per day we are handling? For 100 million users, on an average of 1300 tokens, it means that we will be handling around 130 billion tokens per day. Let's move to the GPU requirement. In GPU requirement, we are assuming that we might be using multiple types of model. Here, GPT-4 class model uses 1.8 trillion parameters and MOE. This needs around 8 H100 replica. Basically, for one model to be hosted, we need 8 machines of H100. H100 is a machine by NVIDIA. We can use multiple type of machines. Assuming we are using NVIDIA H100, it means we need at least 8 machines for this. Now, each replica can handle around 5 QPS of data. We are handling 3500 QPS in a day. This means we need around 700 replicas into 8 machines. That is around 5600 machines is what we require. Now, with the MOE routing efficiency, it can be reduced to around 2000 to 3000 H100s. What about the storage requirements? For storage, average conversation takes about 10 KB of storage. Out of 100 million users with 50 conversation, we multiply it and we get 10 TB of storage conversation. Now, what about the model weights? We are storing the weights of the models. For example, taking GPT-4 class, that it means we need 1.4 TB per replica for the model weight storage. After discussing the storage capacity and back of the envelope estimation, it is very important to discuss about the database schema and the data models. We should discuss about the APIs we will be using. This tells how informed you are about the structure of end-to-end system design. I've taken some of the important tables. Although these might not be the optimal design that should be used in a production system, but good enough for a interview level. We will have a users table which will store the user ID, email, the plan. Plan could be free, pro, or enterprise. Then we can create an ad with the timestamp. We can have the conversation table where we will store the conversation ID, the user ID, the title, the model which we are using, created ad and updated ad. This will be the conversation ID and the user ID will be linked to the messages table. In messages table, we will have message ID, conversation ID, role and content and the token used in this one. After that, we can talk about the tables for usage log. We want to store the logs. We can store the log ID, the user ID, which model was used, input tokens, output token, and the cost and the created time. This way, we handle the end-to-end conversation in a table format. We can talk to the system. I'm assuming we are using REST-based APIs because these are public APIs. This will be a post type with version number, the service, and the method used in that. Here we will be using which model we want to use, the message. We will talk about the role, what we are assuming, what role we are playing, and the content. Explain quantum computing. This is a type of stream because we are doing real-time conversation. And the max token limitation, we can to optimize the usage, we can put max token that the overall conversation does not exceed these number of tokens. Now for response, we will take SSE streaming for token chunks. SSE is server side events. This is the most common pattern used for text-based conversation because it is a one-sided reply and it is good for that. It is less complex than socket-based connection. We can load the messages for the conversation by passing the conversation ID and loading the message IDs. You use a get API for the token usage. It can tell how much token we have used, what was the cost we have spent, and the limit. Now, let me discuss about the high level design. We will have the user interface and the mobile API or any client based interface at the first level. After that first level, we will have the second layer. The second layer is the layer which does the authentication, rate limiting, get the assets from the CDN. Here, there will be API gateway and auth service, which will be used for routing, load balancing, authenticating the user, rate limiting the number of inputs we are having based upon the tier which they fall in. It could be free tier or pro tier. Loading the CDN asset. If a user is sending images or something, we can load it into the CDN nearby to it. After we pass to the second layer, then comes orchestration layer. In the orchestration layer, we decide what we want to send to the GPT or LLM and which model we want to use it. There are different layers and services that will be part of this. The first one is the content moderation. In content moderation, we make sure we are not exposing the PII data. We make sure that we are not sending any bad language or something. We are not asking something that is not allowed by the law of the land. Then we have the context builder. This is the very important part of it because this is the brains where we are modifying the context. We load the previous conversation. Suppose I have asked that what is the election result in Mars. Now for that, it will check in the Postgres database that do we have a similar question. It will make it identify similar questions and then get the data if it has in the Postgres. If it has the data for the election result in Mars, then it will build the context using that. And then based upon that, it will do the model routing. It will send to the model router, and then the model router will decide which model to use. If it's a very simple question, we don't want to use an expensive model for that. We can use simple model for that. But if it is a very complex calculation required or image editing or video editing, then we want to send it to a very advanced model. The tool executor plugin is used for connecting the third-party tools. We want to do MCP connection to third-party tools. If you want to use the Google Drive, then we can configure the MCP configuration and it can read the Google Sheets from there. Or if we want to use some map tools that has MCP configuration, that way we can configure the external tools to be used in this case. After this layer, then happens the actual magic, where we get the response from the LLM. It sends to the relevant LLM inferencing cluster. It's hosted on GPU. It sends back the result either in the form of SSE message or a WebSocket back to the client. That should not be real time. We can have an asynchronous based usage tracker. We pass a message to the Kafka about the usage tracker. That way we can keep the billing on the run. But that is an asynchronous service. We don't want it to be a synchronous based service. That way the system will become very slow. This is a asynchronous service that will keep track of the billing. All right, let's drill down into the next phase. We will discuss each of the components now and go a bit deeper into that. We'll discuss about API gateway and auth flow. Here is the diagram, sequence diagram for that. We will start with the client that he will send a post request with version number of the API and chat with the session ID. The gateway will do the validation. Gateway will first you do the validation using JWT token. Upon receiving, the auth server will send the user ID and the plan, what it is falling into. It can be free, pro, or enterprise. After getting the details about the user, the gateway will check the quota, how much limit is left. Because we have a token limit in terms of ChatGPT or the models which we are using, the rate limiter will check the limit there if there are any tokens left. If it is left, then it will send. Rate limiter will do two types of rate limiting. One is the token usage and one is the number of requests per minute. After that, it will send the request to the orchestrator, where orchestrator will decide which model to use and what will be the output. Upon receiving, The orchestrator will send the response in the form of streams token in SSE format. We already discussed server-side event format. Those will be sent to the gateway, and then gateway will reply with the stream tokens. This is how the flow will happen from API gateway and auth level. Now, moving to the next component is the context builder. Context builder is very important and it is utilized for optimization of the token, cost optimization, so that we don't unnecessarily spend millions of dollars. Nowadays, even though we are using LLMs, it incurs millions of dollars. When we send the new message to the context builder, it loads the context. It might be loading it from the PostgreSQL or Redis if it is very fresh, and it will build a context over it. For example, I ask what is the election result of Mars. It will load the result from the Postgres or Redis, all the information related to the Mars elections, and then who is the president elected in Mars, and then it get the answers. If it hits the Redis, it will build the context layer from there. If not, then it will check in the PostgreSQL. That way, we will have a faster response. After building the context, it will check the number of tokens in the context. If we have limited the context window to 1000 tokens or maybe 400 tokens, so context window is the size of the message which it is actually sending to the LLM. If it is within the limit, if we have 1000 limit for the context window, it will make sure the tokens are less than 1000. If yes, it will send the full context to the LLM. If no, then it will truncate the oldest message to in the context and then create a final prompt. Once it creates a new final prompt, it will send to the model router where it will call the different models and get the response. Now, the next component is the model router and inference scheduler. This is the main component which actually talks to the model and gets you the response. Here's the incoming message. It goes to the model router. Model router does the selection of the models. There might be different types of models. For example, here we are taking GPT 3.5 class 7B, GPT-4 class 70 plus B, or multi-model model. Based upon the query, if it is a simple query or a free tier, we can use an inferior model. If it is a complex query and it's a pro tier user, we can use a better model. Or if it is a vision input, maybe we are inputting an image or a video, it can use a multimodal model. Based upon the type of model we have selected, we will send it to the inference scheduler, where it will schedule it by putting the question in the queue. Now, depending upon the queue depth, the GPU will pick that up first. And if it is a low prior message, the GPU will pick that message a bit later. After that, create a batch of questions. Now, what the GPU will do, it will pick up similar questions or related questions together and send it in batch to the inferencing LLM. And once it sends it to the inferencing LLM, it will get a unique reply for that and it will send the reply for all those questions which are related to. We are saving upon the token and the usage of LLM and it becomes cost efficient. The next component which we will discuss is the content moderation. We are dealing with companies who have PII data like banking systems or credit card data or personal information someone is exposing, or maybe if you're talking on WhatsApp about your personal information, you need to mask that data. What about if you're using a hateful language and that is spreading rumors around certain information that is based upon the policies? We need to do content moderation based upon the company, the region, the city, and all these reasons. Now, for that, we have this content moderation component. And let's see how it works. The user input first inputs into the content moderation that classifies the data. Is it safe or not? If it is not safe, then it will block the data and return the message that there is a policy and we cannot process it. Now, if it is safe, it is sent to LLM inference. LLM inference is a layer, it decides, calls the LLM layer, right? After that, we get the output of the question. Now we need to moderate the output as well. Sometimes LLM reply very brutal truth and we want to moderate that. It might be unsafe for some people. We do another type of moderation here and check if it is safe to stream or no. And based upon the response, we send the response to the user. If you're interviewing for senior engineer roles, it's very important you need to discuss about what all technologies you are using and what are the trade-offs. First, we'll talk about the inferencing engine. The type of options which we have is vLLM, Tensor RT LLM, or Hugging Face TGI. Here you can talk about the page attention, the continuous batching, high throughput. The Tensor RT LLM has an advantage if NVIDIA optimized and fastest on H100 machines. Hugging Face is easy to use and good ecosystem. But the cons are the vLLM, there is a lot of GPU overhead. Because of this, you need a lot of machines. Then in Tensor RT, it is NVIDIA only. You cannot utilize other companies' machines. Then in Hugging Faces, it has a low throughput. It is good for dev level or staging level testing, but not good for production system. Out of all of this, maybe we can choose vLLM or a Tensor RT, and then we can talk about the budgeting. If I want full control over my system, I will choose vLLM. Or if I want a managed control system where the GPU memory and all is managed by other company, I will use the Tensor RT LLM. Coming on to databases, we have three options. One is PostgreSQL, Redis, and S3. Now, PostgreSQL is asset-based database. What do I want to store in that? Most probably the conversation, right? I want to make sure everything is consistent. If I want to save the consistent data, I need to use an asset-based database. For that, I will choose PostgreSQL. Here, I will store the conversations and user. Now, what about Redis? Redis is a great caching machine and it has a property of TTL also. Although it is volatile, but the access to it is very fast. What I think is if I want things that you do not require to be stored for a longer period, I can use Redis, which has a session cache, which can be used for session cache. It can cache the conversation for now, which it can forget later on. S3 is the cheapest form of storage because it's object storage, but the latency is very high. What I will do is, if I want to use S3, I can use it to store the model weights or any file upload. Now, coming on to the messaging system, I have two options, Kafka and S. Now, Kafka is very highly durable. It is open source. It can be optimized according to my own use case. Whereas SQS is managed by AWS. Looking at this, do I need a fast delivery product or I am okay to design the Kafka system and I have the timeline? For that, we can choose based upon what our requirement is and choose between Kafka and SQS. For me, I will use Kafka system because it has more control over how I implement the pipelines as compared to SQS. And if I have a use case where I want to make sure that PII data or sensitive data is not being given to a third party servers or companies, I will prefer Kafka over using SQS. But SQS is good if you have a use case and you have the money for that. Now, the streaming protocol. We have two streaming protocols here, SSE and WebSocket. Both of them are fast. WebSocket is bidirectional. You can send any type of data. And then SSE is primarily used for text type when you want to send one-way text only. SSE is faster because it is just sending the text. We'll prefer SSE for token streaming. Whatever token we are streaming, we'll use SSE protocol for that. Now, if you want to do bidirectional collaboration like Google Docs, in that case, WebSocket is much more better. Here, we will use SSE in this case. Now, after this, as a senior engineer, you need to handle the scaling properties. You need to make sure that the application scales and it is maintainable and reliable. Let's take the scaling strategy. We need to make sure that the data is not lost for a long term. What we will do is we will host the data in multiple regions. We will have multiple region load balancer. Then it will send the data either to the US region, EU region, or APAC region. That we can do load balancing based upon where the request is coming from, or if the data is not available in particular region, then it can search in the other region. At the next level, region level scaling. Now, the next level is the application level scaling. In application level scaling, we will have two types. One is the APIs. APIs will be hosted on Kubernetes. Now, Kubernetes cluster is very important because we can do auto scaling, we can do descaling. It can automatically scale up to the based upon the type of traffic which we have. We can use Kubernetes for the API systems. Now, for GPU inferencing cluster, where we are hosting the GPU, and we want to have multiple models. If one of the models A fails, we are able to use other model so that we can utilize either of the model in absence of one of the models, right? Then the Postgres. In Postgres, we can follow the data replication policy where we have leader and master and slave format in which the leader sends the data to the followers, other regions, and that way the data replication happens. Another strategy is to use read and write replicas. For the write replicas, we keep one database, and for the read replicas, we keep other database. Since we are maintaining a locking system, we don't want the reads to be slowed down because of the locks. Because write logs are mutually exclusive logs. whereas read locks are not mutually exclusive locks. In that case, we will make different systems for read and write replica. We can have faster reads along with the writes. When you discuss about the bottleneck and failures of your own design, then you are a true superstar. Where are some of the bottlenecks of this? One of the bottleneck is GPU memory. We need a lot of GPU memory and it is very expensive. How do we maintain that? We can use a paged attention. Page attention is we melt we do we it is just like a virtual memory where we use multiple parts of a GPU at one go. That way we can optimize the storage and cost. Then second is long context requests. Sometimes you get a very long context. It might be 2000 to 3000 words, whereas few prompts might be of just one sentence that will be 10 tokens or maybe 5 tokens. How do you make sure that the shorter context does not starve because of the long context? Now, for that, what we can do is we can maintain a separate queue for the longer context and smaller queues for the shorter context. That's how the shorter context never go to starve. Third is database write amplification. Fourth bottleneck is cold model loading. Now we want to keep all models in the warm GPU memory. We don't want to put all models in cold model because cold model is difficult to load and slower. If one GPU goes down, we can instantly load the newer GPU because it is already in the warm model. Now, after the bottlenecks, let's talk about some of the failures. Some of the failures could be, what if the inference cluster fails? What if the Postgres fail? And what if the Redis fail? If the inference cluster fail, we can have a multi-region deployment where we can fall back to the other region, or there is better way is we have smaller models for specific requests. If a big model is going down, we can have a replica in the form of smaller model that can be used as a fallback model till the time the other cluster comes back up. Now, what about PostgreSQL? If the PostgreSQL failover is happening, we need to make sure that we are doing appropriate replications. That if one Postgre instance goes down, we can load the other Postgre instance instantly. Redis system, we make sure that we have multiple instances of Redis deployed in multiple regions. This is already handled by Redis nowadays using Redis Sentinel. Now, circuit breaker, if you mention circuit breaker in any of the interview, that will be a plus point. You can reduce the number of GPU error rate. If one GPU is giving an error rate of more than 5%, then you can route to the fallback model till the time you can retrain your GPU and then make it up. If the DB is slow, you can use a Redis cache for that. This way, you can implement the circuit breaker. Now, here are some of the things which you might discuss at advanced levels, especially for companies like Google, Meta, where you interview for senior staff or principal level, where they can ask you a specialized and advanced optimization. Let's go through them. First one is page attention, then speculative decoding, then quantization, prompt caching, async persistence, and request coalescing. Let's discuss about paged attention. Let's talk about paged attention using vLLM. When you send a text message to a LLM or a chat GPT, it stores a memory for that and stores over there. Now, what if for your whole conversation, it blocks one memory space and in between you leave the conversation? For example, it blocked 1 MB of memory. When you started the conversation, you write, hello, how are you? And it replies with the response, and then you leave the conversation. In between, it has blocked 1 MB of space for just for your small conversation. We don't want to have a contiguous memory pages for this. We want to use it like a Lego blocks. We use multiple spaces in the memory to have the same conversation stored, so that you're not blocking the complete block of memory for just one small conversation. And then once a conversation is over, that KV cache space can be reused again. This is page attention. Now, speculative decoding. Certain types of questions. For example, if I want to do a translation, or maybe I want to have a special use case of a LLM. Why do I want to use a big, large LLM which has trillions of parameters? I can use smaller models that are called SLMs, that is called small language model, and use it for my specific use case. After that, once the response is produced by SLM, we can do verification by an LLM. That way, we are making sure that the response is correct and we are not wasting the money and memory resources. Another is quantization. Now, quantization is similar to speculative decoding. Here, we are talking about why not use a smaller size model than using a big size model. based upon the complexity of the task. Many of the use cases we are fine with using smaller models whose size is 2 to 5 times lesser, or we just want to use a small portion of an LLM. That way, we can optimize how much space and how much memory we are using, how much GPU we are using. Next is prompt caching. In prompt caching, we want to cache all the repeated items again. This saves 30 to 50% of the compute. We can save the conversation which we had along with the response for maybe with a time to live of 1 day or 2 days, that all the similar queries can be answered quickly. Now, if I want to answer the election result of Mars, and it is very prevalent that within 2 to 3 days, people will stop asking the result about it. I can store it for a time to live for 2 to 3 days, and then we can reduce it. And that way, I don't have to call LLM again and again. Next is async persistent. Asynchronous persistent is we don't have to write the data in real time to the DB because there will be millions of queries and millions of write queries. I don't want to waste my energy using that. There might be cases when there are too many connections, and because of connection pool, some data might not be written. To manage that, what I will do is I would put the write request in Kafka stream. The database service will pick the request from the Kafka streaming and store it into the memory or the storage space. That way, we are maintaining the number of connection pool and the database writes will never. The last is request coalescing. Now, similar requests can be sent in a batch format, right? You don't want to ask the same question again and again to the LLM. This will inherently increase the GPU usage if you are asking same question again. The cost will be too much and you will be spending millions on same request. Why don't you just use the similar request in a particular time window and send it to LLM? That way you can reply in one go. If you tell about this, you are the top #1 candidate and you are the king. Alright guys, we had discussion about how to design a ChatGPT-like system. I hope you are able to now understand how the system works and will be able to answer. Let me know.